Hello, everyone. Good afternoon, good morning, good evening, wherever you are. Let me welcome you in this new webinar in the series of webinars under the title of Stay Home Webinars. I hope that all of you are healthy and safe from this pandemic situation. Let me welcome my dear friend, Raad Aziz. It is a long time I didn't see him, and it's my pleasure to see him again. Let me say, meet him also face to face again. And this is a good opportunity to learn from him new things. And then from this topic, the Swiss specification, I think it is not known or well known in Iraq because, as you know, maybe the most famous specifications are the American specifications. So I welcome Dr. Raad Aziz again to give the webinar, and I ask him in the beginning to introduce a brief CV for him. Maybe he's known also for his friends in Iraq. So welcome, Dr. Raad, and now the panel is for you.
Thank you very much, Dr. Ali. I'm very grateful for you because this is the first time since 2004 I am in contact with the Iraqi engineers. This is really, I'm very touched by this, your proposal. I'm Abdul Aziz Raad. I'm a civil engineer, graduated from Baghdad University in 1991, master in 1995, and PhD in 2002 in structural engineering. I moved to Switzerland 2004 and start working here using the Swiss specification. I am member with the SIA, Society, Swiss Society for Engineers and Architects, member of IAPSI, which is International Association for Bridge and Structural Engineers, members of FIB, Fédération Internationale de Béton, and also with the Americans, I'm a member with the AASC. Working normally in structural engineering and published several articles, one of them in a paper about my imagination about the Iraqi design code. So today I want to present the maintenance of existing structures according to the Swiss specification SIA 269. This is maybe would be a brief introduction for the Swiss practice in engineering, because maybe you don't have the opportunity to know about the infrastructures and the structural practice in this country. So this webinar is designed in a small introduction about Switzerland, introduction about the infrastructure in Switzerland, both in highway and in roadway, on railroad. Some examples about the bridges in both for highways and railroads, one building, and maybe we'll talk a little bit more about the rehabilitation of the bridge on Château-Chillon. It's a highway bridge on A9. Then we will talk about the code itself, how it's organized, how it the society itself of Swiss Society of for Engineers, and in particular for the family of design code of SCA 260. Then, of course, I will give brief information about the philosophy behind this design code. I also then I will enter to the family of code of SCA 269. Just I want to beg your pardon that I will pronounce SIA in the French way SCA because it's much better, it's much easier for me. So please excuse me for this. Then I have a small numerical example so to show you the importance and the benefits of using this design code. Then some remarks, acknowledgement, and if you have questions, I'll be very happy to answer. So welcome to Switzerland. Switzerland is a small country in the middle of Europe. It's here. Switzerland, we are 41,000 square kilometer, about 8.5 million inhabitants. The most important is the currency is the Swiss franc, which is equal to $1.10. We have a confederation political form that governs 26 cantons. That means each canton has its own specification, its own norms, but everything is under the umbrella of the confederation. For example, the Swiss, the SCI, the specification for concrete and for structures. The capital is Bern, and we are talking in 4 languages: German, French, Italian, and Romansh. I am talking to you from somewhere here between Lausanne and Vevey. And as you can see here in Switzerland, about more than half of the country is the Alps, it's the mountains of Alps, which is a natural barrier between the Northern Europe and Southern Europe. So crossing this Alps is very difficult, a very important part, and we will talk about this later. So the infrastructures to cross this barrier is very important. The most important part of the country is the region of Zurich here, the region of Arc Limanique, the Limanic Arch between Geneva, Lausanne, and Montreux, and in Basel in this area. So this is Switzerland, and for the highways, we have the total highways now exists about 1,700 kilometers. The planned is about 1,900 kilometers. We have some portions that did not finish yet. For example, the portion of A9 between Viège and Brigue, and some autoroutes, some highways in Grison. Few years ago, the portion of Neuchâtel A19 was finished. They are working in some portions about to finish. And as you can see, note that this area is much less dense than this area because, as we said, that's because of the mountains of the Alps. So living here in this area in the Alps, you must work for bridges and tunnels. So about every bureau, every engineering firm must have designed a bridge or a tunnel in their life. So this is just a small detail. The speed limit for the highway is 120 kilometers per hour. The first autoroute, the first highway bridge, highway line was constructed in 1955 between Lucerne, which is here, and it's in this direction. That was the first highway constructed in Switzerland. And then in 1960, the Office Fédéral de Route, c'est-à-dire that means the Confederation Bureau for highways had established that financed all the maintenance, construction of the highways. Just small information, funny information, that the portion between Fribourg and Montreux, it was very important, and it was constructed in 1970, but it was not financed by the Confederation because the Confederation had no money to finance this portion, but the canton itself had the money to do. So the canton itself construct the highway, and then the Confederation paid them later these expenses. We have for highways about 450 tunnels and 4,500 bridges. 12% of them has some defects. This is the news came, it was just 2 years, last year they announced this. 2% of them, that means 90 bridge had considered in bad condition. And they really started to remove them or to rehabilitate them. But fortunately, we have 0 defects. That means 0 alarming problems with the highways. Here we have some examples. I lived in the valley, so therefore I put in the valley, I mean the Canton Valley. Therefore, I put some bridges from this region, and we have the bridge over the Rhone, the river Rhone near Raad. This bridge is can simulate the mountains itself, so therefore you can see it in a strange form. And then we have the other bridge in Sion, near Sion, so the capital of the region. Also one of the cable-stayed bridge, very interesting. Now, I will talk also not only about the bridges and the highways, but on bridges in general. So this one was during our visit for the bridge of Pont de Poya in Fribourg, that actually it was finished and in 2016, and this is during the construction, and you can see the details. And here I want to show you some important bridge. But this one is Sunnyberg, a bridge that was constructed in 1998 and went several hours, because this bridge is the height is the minimum height designed in Switzerland. The designer was Christian Men, who passed away 2 years ago, unfortunately. This bridge about 560 meter long, without any joint, that it's all in one part. This bridge is in Grison, so if you, it's in the way to Davos. So if you go participate for the conference, in the international conference in Davos, you must pass this bridge. Here are some details. I can see the cables. Maybe we have some defects here about its rig, and always under investigation. And you can see it's really an elegant bridge. The designer himself, Christian Men, has designed many bridges in Switzerland, many with real elegance and real, especially in like the pass on Saint-Lon in the valley between near the Alps. And here we can find it was honored to receive an award. It was 1916 in the region of Grison. Then I want to present also Salinas bridge or Burke, which is also in Grison. This bridge was constructed in 1930 by Robert Barres. I will inform you about this. This bridge was the first box girder arch bridge that crossed the mountain. It was in 1991 that was awarded by ACI as ASC actually as a monument, world monument. The total length of the bridge is 132, and the main span is 90 meters. This bridge, as I said, was constructed in 1930. So a few years ago, they did a real renovation for this one to keep it in good shape. You can see the details. Actually, the particular part of this bridge that it was constructed when they don't have the real finance for this bridge. So everything is minimum. Everything is minimum. So you can see the foundation. We don't have foundations here. It's just the arch came to the rock, and that's it. No foundation. Everything. Nothing. And this is, we can, if you pass here, you can find the table about it. And Robert Meyer, this is a photo of him, who founded the bureau T Engineering in Geneva. That was the same bureau that designed the latest suspension bridge in Istanbul in this photo. So this is the history of this bureau. During the rehabilitation of bridges, you can find some funny things. For example, you can touch the old blueprints about the design. You can find some funny ways at that time. For example, the load test, you can see how they did it, and you can see the date and the name of the designer. Just to say that this handsome man is Professor Diaz Vicky from the engineering school in Fribourg. Also, we can find, especially in the region of Grison and Tessin, you can big work for rehabilitation wood bridges, that historical one, such as this one. It was designed by an architect, actually, in 1843, and he was inspired by the design of an engineering, an American design, and they said that it was the most efficient part at that time. So he designed this bridge in the same way. Now, talking about the railway, we have the total length of the railway is 3,100 kilometers. We have 307 tunnels and 6,000 bridges. The first railway was constructed in 1847, and that means very long time, and it was in between Zurich in this area. And the CFF, which is the Chemin de Fer Fédéral, was founded in 1902. So you can understand that many bridges had more than 100 years serving and still serving till this moment, and they need to be rehabilitated, and it needs to be modified because the speed of the trains change, and also the size of the trains. Maybe you heard about the Saint-Gothard tunnel, which is the longest tunnel for railways, about 57 kilometers. It's here in this area. It was opened in 2016, and you can, this photo can taken for the presidents, leaders of European leaders who crossed who came to celebrate this event. The finance of this tunnel came from the Confederation and also from Europe, because, as you know, this area connects the Southern Europe with the Northern Europe. Many bridges, we have new bridges, we have old bridges, such as this one in Freiburg. It was the viaduct of Gantfe, constructed in 1827, and this one, the latest bridge, in about 90 meter near Saint-Maurice, designed by BG Engineering. You can find, especially in the Grison also, many monumental bridges, such as this one, the spiral bridge in Grison, Russia, which is so close to the Austrian bridge borders. And you can see it's very beautiful. This is the train is panoramic, so you can everyone here can see everything. And as a panoramic, everything clear for him. And another example, which is also one of the monuments, the UNESCO named it as monument, historic monument. It was for the Glacier Express. It had been had big works for maintenance in, I think, 2015, 2014, because this is our visit in 2016. Everything is clear and modernized. One of the bridges that very close to me is the Viaduct du Day, which cross the Day River. It is this bridge. I will tell you why it's very interesting for me and maybe for you then later. This bridge was constructed in 1870. The first construction was in 1865, and you can see this paintings about this. The bridge itself had been modified several times. The first one, the first design was this one, the steel bridge, very normal, simple. But in 1910, they decided that they have to reinforce it because the weight of the trains had been changed, so they reinforced it by adding these steel members. Then in 1925, they added arches because the train became so heavy, and because the line here, the railway is the line connect Paris to Lausanne, so it crosses also the mountains of the Jura. It is part of the Orient Express. This bridge is actually a concrete bridge. It's not a masonry, because in 1928, the concrete was a new material, and they had the engineers at that time had doubts about concrete. And you know, Switzerland, they love to be avoid any risk, so they decided to use the concrete inside the arch, but to put the stone outside, just to feel safe, to feel that the stone is here, not just the concrete itself. During the construction, actually the modification of this bridge took two years. I think it was started in 1923 and finished in 1925. The circulation did not stop because this is the artillery of Switzerland for the communication, and you can see how they modified the temporary passage. As we heard from the inhabitants of the small village there, Valor and Orbe, the inhabitants at that time preferred to spend half of the day crossing the river on horses and reaching the next village than crossing the bridge itself on such terrifying situation, terrifying train. You can see also here this part, the scaffolding about to construct the bridge. And the latest modification came in 2011 to 2014. This modification, it was not just modification, it also maintenance for the bridge that dates for more than 100 years. They modify it to respect the new norms came by TGV. TGV is the transport, French transport, high speed. They added about 2.5 meters, they widened the chaussee, the road, 2.5 meters, and modified the chemin itself. So this is a great example about one project had been modified several times. And this is why I like this bridge because it is part of the Orient Express that connect at that time London to Baghdad. Baghdad is here, so you can see the tunnel of Dor. It was here, and the bridge itself, the bridge viaduct today, is just after the tunnel. And you can see it's clearly that the Alps as barriers, and really the infrastructures, the tunnels as primordial, very important to keep people connected. So it is like this this webinar that we are all trying to connect people through the barriers. The only building that I present is the Residential Park in Montpellier. Here, it's not far away from Vevey. It's a building. This is the final form. The building was constructed in I think it was 1909, not 1906. This is the original building, as it was built as an hotel. It was among 9 hotels constructed during the same period of time, because of the English tourists who came to Switzerland at the end of the 19th century, beginning of 20th century. But this building had the top of the building has been suffered a great fire. So in 1920, so they did not have enough money to reconstruct this part. So they kept like this, and it became a school for the hotelery students until 2004. That was this school had finished, and it became empty. This building became empty, and then in 2008 we started a huge renovation for this building. We evacuated all the floors. It was in timber structures, and we changed them to be a concrete slabs to respect the luxury specification or norms that for such type of structures of utilization. The new use for this building is to construct a 24 apartment luxury apartment, and therefore the quality of the building itself must be very important. It must be high class. So we evacuated everything here, and we supported the walls, the masonry walls, the stone work, and at the same time, you will understand that we kept the ground floor untouched, because it is a historical monument. So over this area you can find this and all this construction, and below this area we also added another story here. So the original foundation finished in this part, and we added this part also. It was a huge work, finished in 2014 or 15. The structure finished in 2014. So we kept the walls. We added the part of concrete to have a connection with the walls, and we put the beton, the concrete, everything. The thickness of the slab became 24 centimeters. Finally, the final example is the bridge of or the autoroute, the highway of A9 over the Château-Chillon. This is the chateau. This is one of the castles that was constructed back in the 11th century, and the highway is just here. This one of the most crowded, let we say, crowded autoroute highway in Switzerland, because thousands and thousands. I don't have, unfortunately, I don't have the number, estimation of the number of the vehicles that pass this autoroute, this highway every day. This autoroute has been constructed between 1967 to 1969. This portion exactly over the Château-Chillon was constructed, but finished in 1969. And it had suffered from the concrete from Raad, what we call the alkali reaction. They kept an eye on this bridge to check if really the concrete has defects of this type of defects. And after 2 years of investigation, it was yes. The confirmation was a shock for the authority for autoroute, for the highways, and they decided to rehabilitate it. The rehabilitation work had been done by Professor Eugen Breuwiler, who helped me who gave me this information, because he used a new material for rehabilitation. He used the reinforced ultra high performance concrete, reinforced concrete, and he just added 40 to 50 millimeter, 5 centimeters over the deck to reinforce it first and to protect it from fire, waterproofing, and all necessary reinforcement as a structure part. So Professor Breuwiler, who this material is actually, I think it's a new material, and he was one of the pioneers in this domain. This is a very small example of a photo about the difference between the concrete, the normal concrete, and this tiny layer of ultra high performance concrete. And they decided to add reinforcement here rather than keep it without reinforcement. And to assure the Federation Office for Autoroute, he just mentioned that many research had been done to study this new material, and actually he worked for several projects using this material, the ultra high performance concrete. You can see that he increased the flexure strength for the deck for about 73%, and for the shear about 20%. And the work did not take long time, because it's a very small procedure. It was started in early July and finished in the end of August 2014. And you can, it's just, they kept the circulation, the two circles, because the bridge is in two lane and two way, and they modified the circulation. So all the vehicles in the two-way walk on rule on this part, and here they removed the concrete cover, and reach the reinforcement, the original reinforcement, and then they add the new layer of in French buffet, we call it. The total length of the reinforcement was 2,100 meter, and it cost €2 every square meter, €2. And you will see the process came from this. This is the ready mixture plant, a special one for this material, and you can see the process very simple, because just this machine is the machine that put the layer and continue. You can see the circulation here in two-way, and to continue all the 2,100 meter till the end. The process is very simple. It's like this. This is the new reinforcement, and some photos that to add to see the procedure. And then it was finished. It was 2014 that everything has been finished. It was finished here. This is during our visit in 2015. Now, to give an idea about what the importance of maintenance of structures, you can see here that infrastructure, the value of infrastructure in Switzerland is, we counted about 813 billion Swiss francs, about 108,000 Swiss francs per each person, and annually it's 19 billion. The cost of it. Then we have for the residential, it's just a comparison between the residential construction. The value of the value residence is about 1,500 billion Swiss francs. That means 200,000 francs for each person. 50% of that since 1970, because the huge boom, economical boom here. And if we are talking an annual maintenance and for residential construction, 10 billion and a half each year. That means per year 1,350 each one. The planned project for infrastructure between 2010 and 2030, it was planned as 65 billion Swiss franc every year. That means 8,500 Swiss franc every year. So you can see, you can feel the importance of the investment in this sector. All the infrastructure, as I mentioned, you saw several projects constructed during 19th century, and most of them had a strategic importance. So we need to maintain these projects because these objects, because we have either higher level live load, we have the fatigue, we have problems with concrete. The durability of materials had to pay attention on this. So this is the important part. Now I can come to the how all that can come, how all that can be managed. So all the construction for architects and engineers organized and governed by the Society Suisse. We call it SIA, which means Schweizerische Ingenieur und Architekturen, or in French, Société Suisse des Ingénieurs et des Architectes. As I mentioned, I prefer to pronounce it not as SIA because it's difficult for me. I think it's better to keep, I keep pronounce it as SIA, so please don't be upset from me. Some historical information about the SCA. It was founded in 1837 in Aarau, New Zurich, and we are about 16,000 members. About 2/3 of us are architects, and the rest is civil engineers or engineers in general, but civil engineers and mechanical engineers. The first publication for specification came in 1877, and I will mention that the first honorary president of the SCA is General Henry Dufour. If you maybe don't know him, he's not just an engineer, he is a politician, he had general in the army, and he had a very important role to shape Switzerland, not as engineering part, but at political part, at a political shape. So that means that the shape of Switzerland politically is formed by him and, of course, his campaign. So he was the first honorary member. Finally, we arrived to the specifications that governs the structure engineers. as you have in Iraq, the ACI 318. In Switzerland, we use the SCI 260, which is the family, it's a whole family of norms, first published in 2003, replacing the old specifications for structural engineers. That was SCI 160. It was the old fashion norm. And since 2003, we arrived to the new philosophy and new form of specifications that approach a little bit for the European code. So it was the period that they tried to approach each other. So we are working now for the third revision of this specification. It was published in 2013. I'm talking about the new for new structures, and it was organized in this way. The 260 is the basics that I will focus on this, and then 261 for action on structures, 262 for concrete, 63 for steel structures, 64 for composites, steel and concrete, for timber and masonry, and then finally for geotechnical design, we are working on with 267. This code using limited state, I think it's the same thing with, I don't know, maybe with the ACI, I'm not sure, but it's a typical limited state design code. What that means, we have both of them, the ultimate limited state, ULS, for security of structures. And we have the serviceability limited state that's for deflection, cracks, and etc. I will focus on more about the ultimate limited state that we have 4 types of limited state. The first for stability, the second for the resistance of structure that we normally use it the most, and type 3 for the resistance with the ground. That means the relation between the structure and the foundation. And then number 4 is for the type 4, number 4 fatigue. I will concentrate more about the ultimate limit state type 2, which is for security of structures. We have the typical form of relation between the effects of action and the resistance of the structure. Here, E means the effect of the action, and we love to call the loads as action more than loads. For the resistance, we have RD, and sorry, you can see that both of them we have a small d. That means it's a design value. Design value, that means we have the with factor of safety. It's not alone. So if we are talking about the dimensioning, which is design, we love to call it dimensioning, or in French, dimensionnement. We have the combination of this part. That means we are using the dead load with the factor of safety of dead load. We have the pre-stressing, if you have pre-stressing, with the factor of safety of pre-stressing. And we have here, I will pay your attention that we have first work with the most important live load first with its factor of safety, and the rest of the live loads, the other effects with reduction. Just small example, if we have a roof for a building and we have live load, we have dead load, we have the snow load. So if the snow load is higher than live load, so we will use QK1 as the important in this, and use the factor of safety, the full factor of safety of this part. Rather, the live load is, if its live load is much less than the snow load, so we can use some reduction. Of course, we have some logic here. If we have, if the roof of the building is full of ice, nobody will come outside. Will be on their top. So, but therefore we have some factor of safety here. This table gives you the factor of safety for everything for dead load, if it's action unfavorable, and if it's favorable, and for live load also. Just pay attention of this value because we will need it later. This table, just to show you the factor of safety, the reduction of C for live loads, and we will tell you why we use this, this reduction. Maybe you don't have in ACI, the American codes don't use this type. Maybe this is a good discussion between us. Now for the ultimate limit state, if you are talking about the resistance of the members, you know that the effects must be less than the resistance. If you are talking about the resistance, the design value of resistance, you have this combination. This came from the code. We have the design code for the for concrete, which must be 1.5, and we have the design code for a design factor of safety for steel with an 1.15. As an example, I just took the two tables here and then the next slide about for pedestrian bridge in Freiburg. It was a small one, so we have to put all the factor of safety in table to understand what's going on and to keep everything clear to us, so we can find the values here with the self weight and the model, the load, the first one, the snow, the wind, and temperature. We have all these factor of safety, and sorry, we are going to the next tab. If you are using Diana, for example, the software, we don't need to write this this table, but we were obliged for the authority to present that we checked all the load combination, and therefore you can see how it's happened. It's an example of how it works. Now, finally, we arrived to our destination. It is the new norm for the existing structures at ACI 269. It's a new design code. I just want to mention that the committee of this design code, the president of the committee is Professor Eugen Breviller, and members of it, Professor Thomas Vogel and Dr. Paul Lossinger. Just to mention that Paul Lossinger was a member of the committee for this code, was the consultant engineer for Haifa Street project in Baghdad back in 1980s. And every time he has a big smile. Remember all the projects. So the design code, maybe it will be the first, as I know, it will be the first design code for structural engineers for existing structure. Correct me if you have other information, please. So if you have an existing structure, you don't need to work with the 260, but you can use the 269. This family came in several portions. The first one is the basic. Number one is for existing structure and action. That means loading. We call loading action in Switzerland. And from 2 to 6, we are talking about the existing structure for concrete, steel, composite, timber, and masonry. Then number 7 is for geotechnique. Number 8, this design code for the earthquake, the existing structure with earthquakes. And it came later, came at the end of 2017. So this is the family of this code. And the basics, the references of this code is presented here, because to establish this code, they need the previous code, that such as the ACI 469, the old one, which is talking just about how the procedure, but not in the, as the structural design. We will show you later. And of course, the other codes, especially the ISO, maybe I did not put it's here, the ISO 13822, that talking about safety of structures. Maybe I can add the spirit of part of the code came from JCSS, the Joint Committee on Safety, on Structural Safety, which is Joint Committee, their code, the model code for JCSS. JCSS is part of the YAPSI organization. YAPSI is International Association for Bridge and Structural Engineers, based here in Zurich. This is the content. Through the content, you can follow the procedure. That means you don't miss the value. Huge attention came to focus on the terminology, because by treating existing structures, we have to be very careful to mention certain terms such as examination or updating. The flowchart for the work, I will not enter here in this more detail, but I can just say that at the end, the SCR 269 give you the tools that allowed you to take the decision if you are do nothing, or if you have to remove the structure to replace it with another thing, or you have to urgent measures for such as some modifications or maintenance properties, and if you have to just keep an eye on it because something is not working well. We have two types of examination for the structures, the general examination and the detailed examination. Maybe I have 10 minutes to set, so I have to walk a little bit faster. The requirements for the code, the 269 is the structural safety, the serviceability, and the proportionality of intervention, which is we will mention that, which is not exist in the for structures and as a new structures. Update is the first step for the procedure is first of all you understand the new needs for the structures. For example, the owner of the bridge or the owner of the building or the state, the condition of the building as a material for concrete or steel or the reinforcement. This is the first step. The second step is mostly by the engineer himself, is to update the loads. For example, a bridge constructed in 1860, the live load is not the same in 2020. So you have to update all this information, and most important is to also to update the structural model. If you have, if the structure had developed a plastic hinge or anything, or it behaved not as the designer and at the beginning had thought about, imagined this structure. So the second step is to update the structure. Then you go to the analysis part, and here we have two analysis. The procedure for the analysis is a progressive. Has a progressive shape. That means we start with a simple information, simple understanding, for simple calculation for the structures, and what we call using the deterministic verification. What I mean by deterministic verification, I mean we are using the same concept, of the limited state design code. That means with factor of safety. But as you see, the factor of safety here is everything has been updated. ACT, so that means actualized. That means updated. We are using now, since it's an existing structure, we are using exactly the same limited state condition, but we turn it in another way. We are using now, we calculate the degree of conformity, N, which is the ratio between the resistant and the effect. The ideals to be larger than 1. If less than 1, that means it's not correct, because that means the effect is bigger and bigger than the resistance. The N can give you an idea about how much you are close or far away from the normal. If it show you 2, that means you are perfect, because the resistance is double the effect. If it show you 0.9, that means you need just some small efforts to reach the normality. The 2 windows here show you it's that same limited state formula, but everything is actualized. For the factor of safety, we are just have a small modification. We can use the same with 260 only for the live load, for the dead load. We reduce it to 1.2, not 1.35. Why? How? That means here's some reduction here. Why we have doing that? Because when you design a new structure, you have some uncertainties about the geometry of your object. So the geometry, you don't know if on site they will do this slab thickness the same as you design. Maybe they will do it less than what you design. So, but for existing structure, the situation is not the same, because the structure is there. All what you need is to go to the site and measure the geometry, measure that slab thickness. So therefore, the uncertainties of the structures is reduced. So we can reduce to 1.2. This came from some studies. Probabilistic studies. So this is the first part. If you are talking about for serviceability, nothing has changed because it's the same, but we focus more about the ultimate limited state. Now, when you check the analysis of your existing project and you find that your structure is not confirmed, that means the condition, the limited state condition I mentioned here did not satisfy. That means N is less than 1. You don't have to rush and ask the owners that you need to reinforce the structure, because you can give it another chance. And this other chance is by using the probability verification for the structure. Here, I want to stop a little bit and go outside to discuss the original, the foundation of this approach. This approach is a probabilistic approach. That means it's more statistical, based on the work of model code of JCSS, as I said before, the Joint Committee on Structural Safety. So it's a new structure, a new type. Maybe we are not familiar with this type of analysis. To clarify, the structural engineers, we are working with all the factors, all the values that we are working on are not a fixed value. All of them came from statistical studies. That means the live load in your bureau or live load in your living room. If you are working at 2 kilonewton square meter, if you measure the weight of the live load now, the time, you will never reach the 2 kilonewton square meter. because the 2 kilonewtons square meter is actually the value that you have. The structure of your living room will have the chance 1 to the 10 to the power of -5, and every year that will have exceed this value. So it's a statistical value. It's the statistical concept. This figure here explains exactly what's going on, and this line means the 70% of the live load of the value. Therefore, we have the factors of reduction factors. The same thing with the resistance. If we are saying that the concrete in your structure is 30 megapascal, that never means that all the points in your structure have 30 megapascal, but it's a statistical meaning. That means that the 30 megapascal means that 5% of your wall structure concrete is less than this value. And here the main study of the JCSS, that means this curve means the resistance should be bigger than the effects, and the only part which is the evaluation of risk came from this part. Just Dr. Ali, I'm afraid that I arrived to 1 hour, so can I have another 5 minutes?
Yes, no problem. Go ahead.
Okay, perfect. Thank you. So this is the concept of the probabilistic study, and you can give a chance for your structure, your existing structure, to go further. In other words, if they allowed me to say this, what I mean by probability verification, that you will drop the factor of safety, that you have it from the code, special for by deterministic method, and you can search for your factor of safety, the roots of factor of safety that fits exactly your structure and your condition, your situation. So what we have here, they found that sorry, I just forget to say that it's not recommended to use this method, the probabilistic method, if you don't have a clear statistical information about your structures. So if you have already statistical information about your structure, your infrastructure, go ahead, because you have the values, the real values. But if you don't have, better go to your structure, infrastructure, and study them and come to develop it. So what they found through the probabilistic verification, they found that the action for permanent structures and the stiffness behave as a normal distribution. They found that the variable for accidental and variable action behave as a Gumbel distribution. They found that the resistance, it can behave either normal or log normal distribution. So we can use this information. This came from the study of JCSS. Do the Iraqi infrastructure follow exactly the same way? This is, you can answer these questions. And I will tell you that many people are curious what you will find. So if you are talking about the normal distribution, you have these equations. These values are pure statistical information. I just will focus on beta 0 later, what it means, but the others are statistical from your situation. You have the, so I will go faster. So this distribution is for the dead load. If you are talking about live load, we are using, sorry, for Gumbel, yes, Gumbel distribution is for the live load. And for the log normal distribution, you can use this one. I want to show you what means beta 0. Sorry, this is one of the values that proposed by ACI 269. Beta zero, so I do not have much time to explain, but beta zero is reliability index. It's the target reliability index, beta zero. What it means exactly? That means how much you rely on your infrastructure, on this bridge, or on this tunnel or this slab. So how much you rely. The reliability is the contrary of the risk. So this table give you the values of the reliability that you can use it for the equations to determine in your probability verification. The normal, the usual part is 4.2, but it depends on your structure. So you need to calculate the efficiency of intervention. The efficiency of intervention is the proportion between the reduction of the risk that you have in because of your work, because of your intervention for the structure, and the safety cost. That means if you have a road and a curved road, and you have a project to add a guardrail to protect the road, so the project will cost you 1 million, and according to the estimation that we will reduce the risk, annual risk, for 1 million also. So the efficiency of your intervention is 1. It came in this part. So you can understand what I'm talking. So if you have efficiency of intervention is higher than 2, that means the intervention that you do for the structure will reduce double the cost of your intervention. That means it's very high important. It's an important project for you. Imagine the tunnel of Gotthard. If something had happened, what the reduction if you do some intervention here. On the other side, the coefficient of consequences for failure is another value. It's another factor. So it's the proportion between the cost of the event of the failure itself. The bridge came down, and so the cost of this failure, how much, and the cost of the restoration of the following the failure. So the higher that means the more important. So according to these, you have the guideline how to choose the index of reliability index, how to choose the target reliability index. If the efficiency of intervention is very high and the coefficient C is high, so you have to rely really on your project, on your structure. So it's very important. Therefore, they increase the effects. Just to mention that this table came directly from the work of JCSS, the model code, but the model code they used the risk value, not the reliability value. So if you are the two way are the same, because the at the end it's the same thing. So again, this is what I'm talking about, the proportions of safety and reduction. Now, to give you an idea what's going on with SCR 269, I will have a small example about a simply supported reinforced concrete beam. The span is 6 meters. The height is 30 centimeters and 20 centimeters the width. The old live load for each meter long is about it's 9.6 kilonewton every meter, and the new live load that we will update the live load arrive to 12.2. You have the type of concrete and reinforcement. So if we are working with the original bridge as original beam as a new structure, so everything is okay, because the effect of the moment is less than the resistance of the concrete. We note that we are using this. If this beam is an existent structure, so you don't have to use this one because the factor of safety is different. But if you use it, if you use the code for new structures, you'll find it's not okay because you are using the factor of safety 1.35 that consider some uncertainties about the geometry of this structure. But if you use the code, the new code 269, you can reduce the factor of safety. So you can find here some better, the effect is start to approach, but it's still not okay. So you don't have to declare that you need to reinforce this project. You can give it another chance by calculating for the first time only the action as a semi-probabilistic part. So you do the calculation and you can note that we don't have the factor of safety as here. It's because it came directly without factor of safety. It's already calculated. So you can see you reduce the factor of safety. Here, the calculation came as a deterministic evaluation for resistance with semi-probabilistic action, but it's still not okay, but it's very close. Now, if you use both the action and the resistance as using the semi-probabilistic work, so you can find that really you are in a good position. Actually, I forget to say that I used a medium target index for reliability index in this project. So if you have a higher target index for reliability, maybe it will not pass. So this is a small example about what's going on. Here I want to give some, sorry for I took 10 minutes more than what the presentation, but I want to finish with some remarks that no need to say the importance of about the maintenance of existing structures, especially maybe in Iraq, because you have many problems with wars and problems with the rehabilitation. I think the code ACI 269 is an original code. It's a progressive. Maybe it is the only design code for structural engineering for existing structures. I don't know. Correct me if I'm not. I have some ignorance about other design codes. I feel it's important to educate and to train engineers talking about this type of studies, as this webinar is part of this effort. Here I highlight the structural, the factor of safety, how we can calculate factor of safety using the probability and probabilistic approach. This is very interesting for the design code for maybe for Iraq, because you can reach how much the factor of safety you need. The other part I want to focus on is the know your structure. The words of the wisdom word came from the East. Know yourself. Here I said that know your infrastructure. What I mean about know your infrastructure, that you have to know how much they are safe, or how much they must be safe, and how you can do the best to understand them. That means you have to master them. And finally, I'm very happy to, and through this webinar, that I tried to open the window between the two extreme of the engineering practice, between the Swiss practice that they don't accept risks, they don't do risks, and they have ultra conservative approach, and with maybe Iraq practice that maybe accept more risk. I'm very happy. We are very curious what will happen if we allow both of you to talk, both sides to talk and to share some information. And finally, I would like to acknowledge thanks Professor Egun Breviller from École Polytechnique Fédérale de Lausanne, our Swiss Federation Institute of Technology, who is the president of the SCIA 260 for his time and the information that he gave me. By the way, he is one of the pioneers in developing the ultra high performance reinforced concrete. And would like to thank the Association Patrimoine de Fil de l'Eau, ORB, for allowing me to publish the photos and the information about the viaduct today, because it was part of our work, their work. And finally, I would like to thank you, Ali, to give me this opportunity. And I'm very sorry to take 15 minutes more than that. And thank you very much.
Thank you very much, friend Raad, for this valuable information, and not only valuable, but it's new for me. I don't know what about the other audience. Let us start the questions, and the first question is from Dr. Rafi Suleiman from University of Burke. Depending on what criteria the design of an existing structure should be updated.
First of all, the criteria, the first criteria came from the owners. For example, if the owner said that I want this bridge to serve another 15 years, and I want to increase the live load to certain level. So the first part came from the owners. Then the engineers came from the criteria, from the engineers to evaluate other problems or other loadings that maybe not concerned by the owner, and then we advance with this part. The code ACI 269 give you the tools. You have the index of reliability index, the target, but it's that you can see what's going on. You have the N value to see how much you are close or far away from the normality. So you have all these criteria, and you can use them by wisdom, by discussion with the owner. Some owners, they no, we have to demolish everything. I have the money, but in some cases, the owners are not so. They want to search more and more. I don't know if I answered correctly
Thank you. Also, let me open, because of the limited number of the audience, also open the panel for others, especially our professor, Dr. Raad and Dr. Yes, but let me first to allow them to open the microphones and then start comment about this thing, about this topic. So, Dr. Saad, Dr. Riyad, other attendees, if you have any comment, you can raise hand and start talking with Raad.
Assalamu alaikum.
Alaikum salam. You're welcome.
Dr. Raad, thank you very much for this impressive presentation. I really enjoyed it. It's a bit night here, so two things I don't miss. The ACI webinars that Dr. Ali is organizing, and especially coming from Switzerland, you, Dr. Raad. So it's very much worth my staying late. It's, Swiss engineering is it's very impressive. I've been working with EMPA in Zurich, Dr. Raad, I'm sure that you know them, and some work we have done with the EPFL down in Lausanne. We have got joint projects with EMPA on strengthening of metallic steel bridges. And two projects that we have completed. One is in Zurich and the other one here in Melbourne, Australia. It's a joint work that we have got. What's impressive about Swiss engineering when I say that is that the level of detail that they go into, that they do not leave any detail not attended to. and which is quite impressive. And it's quite impressive the way you have explained the SIA, as you say, regulations in terms of the level of detail that they have put in the Swiss code. So let me ask you two questions, Dr. Raad. One is non-technical. How have you been able to maintain such good English in a French environment? And the question I have is the Swiss code versus the Euro code. So are the Swiss going to stick with the Swiss code, or are they going to align it with the Euro code? Thank you.
So Raad, please unmute yourself.
Okay.
Yeah.
Thank you very much. I'm very, very happy to meet Dr. Yadlin Hadi. It was actually a surprise for me. Thank you very much, Dr. for your comments. And first of all, about my English, well, I read a lot in English, and I write in English. I published some literary between us, to not say anybody, to tell anybody, but I write some.
And your Iraqi bases are very strong because you're English from Iraq.
About the relation between the European code and the Swiss code. Well, the Swiss code, you have to understand the mentality of the Swiss people. They are people from the mountains. That means they are really feel secure among their mountains. Just to tell you something about when they started to construct the railways in Switzerland in the 19th century, it was an English engineer who came here, and he was shocked when he started to cross valley after valley, and he noted that people in some valleys did not know what's going on, what's behind the mountain. They are just in their environment. So the same thing happened with the code, with the Euro code, and we have now in this Sunday we have some political votation for the relation between Swiss and Europe. For the design code, they decided to approach the Euro code when in 2013. I think actually the fruits of that attempt came in 2003, because they noted that the Swiss code or the Swiss practice is totally different than the Euro code. I mean, totally different. Not in the mean of the spirit of the philosophic and the scientific background, but on the marketing of structural engineering. That means, just a small example, in Switzerland, never used the bar diameter less than 8 millimeter. We have to forget that. But in Eurocode in France and in Germany and Italy, they use 6 diameter, 6 and sometimes 4. I don't know. They have some approach this way. And Switzerland, they don't have diameter 25 millimeter, but they have 26 millimeter. So they try to have some difference between the European, because the Swiss market is very rich, very high paid, but they want to protect it from the others, from the Europeans. I remember one time I discussed with the Professor Manfred Hirt. I think you know him very well, and he told me the first. I have this his expression in it's always in my mind. He told me, "We are not Europe. We are not Europe. Europe, they have the design code. They have like this, all these design code, but we have like this." And this is exactly what's going on, because they use the mentality is not to regularize everything, to leave the engineer do his work by his knowledge, but not to manage everything. maybe I take a long time about this, but always I ask also, I remember with the Professor Manfred Hirt, he told me that good engineer never needs a design code. So this is the mentality, the mentality of the Swiss engineers in this direction. Therefore, they try to approach them as regularized, not to be so much brutal differences between them, but they try to smooth something, but still they have a huge more mentality differences.
Thanks very much.
Yes, thank you, Dr. Raad. And I apologize from our attendees that I focused on our esteemed professors. We learned everything engineering from our professors like Dr. Qais. Dr. Qais, if you have any comment about the lecture, we are happy that we have you now at this webinar. Also, we have Dr. Saad Al-Ta'an, if you have any comment about this webinar. Okay, thank you. Any other comment from our friends attending the webinar? Any question? In fact, maybe the main question is about the relationship between the European code and the Swiss code, and Dr. Raad precede us in this important question, because as I know that every country in Europe have a national annex. So I think you have a national annex, Dr. Raad, right?
No, we don't have, because we don't use the Eurocode. We use only the SCA. The SCA code, the Schweiz Ingenieur and Architekturen, or Société Suisse d'Ingénierie et d'Architecture. So this is the code. This is the document for the code for the existing structures. Mm-hmm. So no, we don't have annex because they are Europe. We are the Swiss.
Let me ask you about this new code, as you know that. You mentioned that maybe this is the only code. Also, for my knowledge, I didn't see that there is a code in about 8 volumes just dealing with existing structures. So it is, I think, maybe devoted mainly for not only repair of the existing structure, but only strengthening, as you mentioned in the example, that we, for example, we have a building and want to, for example, increase, or that maybe bridge, increase the loading in this building, or change the function, and this change will also increase the loading. So you have 8 volumes of this code, and you recalculate everything, maybe from the properties to the actions and also to other things. So it looks really amazing thing.
Well, the code itself, the 2060, is not a big one. It's a very small one, but it gives you the tools to have the help to have the decision to keep the project keep the structure without reinforcement, to reinforce it, or to keep an eye on it, to investigate it, or to monitoring, the monitoring work, or at the worst case is the decision you have to remove it totally. So you, through the code SCA 269, you have all the tools, especially for the existing structures, how to react and how to do. And I will tell you, maybe it's secret between us. Professor Jürgen Broviller, who is implied on this in this design code, is very curious if what will happen if you in Iraq study this type of doing this type of studies about these structures. I don't know if maybe it's interesting, or maybe I don't know if you.
Yes, we need, of course, as you mentioned, that Iraq, everything is changeable, not only because of wars, and also maybe you build a hospital, maybe after 1 year you change it for a school and something like that. So I think such a type of code is very important. Let me go in more detail, for Raad. For example, volume 2 is dealing with the actions, different types of the actions. And volume 2, maybe in the European code, also dealing with the actions. So
Exactly.
what is the difference between the actions in let me say, the new existing structure in comparison with that new structure? So what is new information?
No, for the action is there no difference, but what's for the action we have to actualize the structure, the existing structure, for the actions of nowadays, now and here. So you don't need to search for the older part, but for the code 269/2, it's for concrete. They give you a big information and about the historical of the values in the design codes. For example, if you are working for a structure that was constructed in 1950s, so you have through the table, you have all the values that they used at that time. So you can have an idea what we are going on, what's going on inside the structures, and you can base your analysis and calculations for the resistance based on this value. Maybe I can, sorry, I'm not, I'll show you here. You can see the design codes, just this one. And if you, Dr. Hilton will be happy to say that with the Europeans, they have this this type of design code. So for the concrete, you have at the end tables about all the values from the design codes from several years, and therefore you have all the informations here. And that, I don't know, maybe in Iraq, maybe it's very interesting, especially during 1990s, many projects had done with the reinforcement that came from, not from the type of steel is different than the normal one. I mean,
yeah, we have a question here from Dr. Saad Al-Ta'an that are there great differences between the SAI code and the European or the German code? Do you compare those codes with the SAI code?
Of course. No big differences between the Swiss code and the European code. The only different than European code, you have more detailed information. That means if you have lapsed length for lapse, you have more information, more details, more requirements. Rather in Swiss code, they don't mention, because they said that you are engineer, you must know what you do. So this is the mentality. This is good and this is bad also. This is, why? Because when I came here, I have to learn. So I try to search for documents that are talking about the design code, but nothing, because you must know. And therefore it was an effort to understand what's going on.
Yes. Other questions from Saif Halim. The question has relation between SIA code with Iraqi nature related to the, for example, earthquake risk and so on.
Well, for earthquake the design code is 262/8.
Yes.
We had 4 seismic zones in Switzerland. 3 of them is not dangerous. One of them, the zone 3B, is dangerous, which is in the valley and near Zurich, not Zurich, not near Basel. We have problems here, but we don't know what the Iraqi design code. I don't know the Iraqi situation, if it's okay or no, I'm not sure. But for the design code in Switzerland for earthquake, focus on the concept of the building itself. That means if you construct a building, design a building in the valley. You must respect the dimensions. You have to prove that you use the right place for the concrete members that resist the earthquake, the lateral forces. So we have some restrictions, heavy restrictions about the construction of buildings for seismic loadings.
Yes, thank you very much, Dr. Raad, and also thank you for all attendees to spend this time. We feel very short because of the Swiss code. It's the new idea about this code. So I think this is also maybe a good start for more dialogue, as you mentioned, between Iraqi and Swiss engineers. And we hope that we have the professor, the chairman of the Swiss code 269, maybe the next speaker in the coming weeks.
I hope.
Thank you again, Dr. Raad. Thank you for Dr. Riyad, all other professors and friends and attendees, and see you later in the next webinar. Thank you very much.
Thank you very much. Thank you.
Thank you very much.
Bye bye. Thank you very much. Thank you.